Hi, I'm David Newman from Wells Fargo Bank, and I'm going to introduce you to knowledge graphs and ontology in banking. First of all, new frontiers in innovation require investments in new foundational building blocks. First, we have to create a brand new model that is highly expressive. Secondly, we utilize novel technologies to exploit that model in order to generate certain innovations. As an example, the mapping of the human genome is an example of creating a first of a kind model. DNA sequencing technologies are examples of exploiting that model with new technology to reintegrate the fragmented parts of DNA in order to get a holistic view so that new innovations could be created once we apply that model and technologies such as the recent mRNA vaccine, personalized medicine, and cancer genomics. Similarly to this kind of breakthrough, we need something in banking and finance that does the same kind of thing. And we've started that with knowledge graph technology. We're able to map, we'll call it the financial genome, using knowledge graph models. New technology has been created to leverage these new models that will basically reintegrate the fragmented parts of data within the enterprise in order to apply new innovations to get much more holistic views of customer information, better ways of solving financial crimes, fulfilling regulatory reporting and compliance requirements, improvements in data management, improvements in identity resolution. Knowledge graph really is going to be the way forward with data. Let's look at this also in a broader spectrum where at the bottom of this trajectory is things that humans understand, and at the very top are things that machines understand. And in parallel, we can see something that we'll call model expressivity, which is directly related to the power of any information model. So back in 1970, over 50 years ago, the prevailing paradigm that is applied today for data is the relational model that everyone is familiar with. Strings and numbers within columns and tables within databases. This has carried us forward to today and will carry us beyond, but the level of expressivity is very, very minimal compared to what is really achievable. With the advent of ontologies and knowledge graph models in the early 2000s, with the emergence of knowledge representation and reasoning, which is actually an aspect of AI, we're able to leverage new formal logical approaches to understand and describe concepts that can be linked to data. So in this view, we leverage a graph where the nodes represent things or concepts, and these lines or edges to other nodes represent labeled predicates or relationships that connect these things together in a meaningful way that adds to a high degree of expressivity and data linkage. Then moving forward with the convergence of knowledge representation and reasoning and machine learning, we're able to apply these algorithms, such as link prediction algorithms and others, in order to add connections between these nodes to predict relationships, as well as to make inferences or predictions on new nodes that basically organize and classify many of the other nodes. And we'll call this predicted things or knowledge graph 2.0. And then to more recent times, we move to what we would call vectorized things, which is actually a way of converging knowledge representation and reasoning, machine learning and deep learning and natural language processing, all of it together to train on many of these earlier types of knowledge graph models to transform things that would be pulled off of a disk in a conventional database into numeric representations, which we call knowledge graph embeddings or vectorized things, that allow machine learning algorithms to much more effectively perform analytics with the data that would be in a knowledge graph. And this is a very powerful capability and is much more aligned with things that machines can understand. So with knowledge graph, we now begin to think of our data as things, not strings, to paraphrase Google. So knowledge graph really is a very powerful way to attain that elusive vision of the customer 360. So given a problem where we have many different lines of businesses within a bank that describe a party or a customer in many, many different ways that today are very problematic in terms of getting a holistic view of that party. For example, we might have a commercial banking account where Acme Widgets Incorporated is viewed as a customer, and that is all represented in a relational database. We might have a credit card merchant line of business where Acme Widgets Corp is represented as the merchant, and you can see they'll, to a human, we can assume they're probably the same entity, but to the system, it is identified very differently, and we may miss that. Then there may even be a third line of business that might have as a guarantor of a loan, Acme Widgets Inc. And then we may work with a vendor, Acme Widgets itself, and we have four representations of the same thing, but within our current environments, these different parties are viewed independently. However, the goal of the business would be to see each of these currently differently viewed parties as the same party, so that we could look at more holistic views of that customer in order to gain better analytics and better support the customer experience so they don't enter redundant information all the time. And for many various use cases, we need within a bank to see that holistic view of the customer. With the advent of knowledge graph, because of the new capabilities that I mentioned a little earlier, particularly in the area of identity resolution, as well as the emergence of what we would call the enterprise knowledge graph. The goal is to be able to look at the disparate information that exists in many of the siloed lines of businesses and be able to draw inferences and predictions in order to determine which of these are really the same. So essentially, by performing identity resolution, we're able to link and align many of these disparate parties together. So knowledge graph allows us to ingest data from different sources, map that disparate data to a common model, perform certain standardized validation, and then to perform certain enrichments, which includes identity resolution, where a capability that will be a very powerful emerging capability is this notion of creating this registry of digital twins, where identity resolution links different parties together, all the different representations of Acme widgets, into a common single first-class object with a common single web addressable unique identity that can then be looked up, as well as not only different parties, but different kinds of assets, different kinds of institutions can all benefit from this notion of identity resolution into this first-class thing where we can create a single entity that will basically reflect all the variously different names of identifying Acme widgets, but will add some additional knowledge from the knowledge graph that this entity is a corporation. It has a certain date of incorporation. It also is tied to a particular physical address. Like in the real world, there is only one thing for that physical address that will exist in a city. That city will exist in a state. That state will exist in a country. And we could see a graph or a hierarchy of relationships of first-class things similar to the real world, rather than looking at many, many different unrelated strings. So when we move to things, we get greater connectivity. And then the different lines of businesses are also different kinds of graphs that can link to these entities and be able to iterate through these graphs in order to create a very holistic view and a very powerful way of working with information. So with the advent of knowledge graphs, enterprise knowledge graphs, the application of machine learning, deep learning, knowledge graph embeddings, we're going to be able to make great progress and great strides in being able to identify information, uniquely integrate and link into information into a holistic view, and further enrich information and gain new insights by leveraging machine learning methods, knowledge graph embeddings. And this will be a very powerful forward move for the enterprise. Thank you very much.
Hi, everyone, and thank you for attending this session. Today, I will be talking about building domain-specific knowledge graphs, or KGs, from text. My name is Mayank Kejriwal, and I am a research assistant professor at the University of Southern California. Although many of us likely know the definition of a KG already, for those who don't, I would like to start with a brief introduction and visualization of a KG. Put simply, a KG is a set of triples where each triple is of the form head entity, relationship, tail entity. In this graph visualization, an example would be Steve Jobs, fan of Bob Dylan. Entities are vertices, while relationships are the labeled edges. They also yields a graph theoretic definition of a KG as a multi-relational directed labeled graph with semantics. Semantics in a KG may be generic or common sense as embodied by the Google Knowledge Graph, which is one of the earliest examples of a large-scale KG and is now commonly used in its search engine. Today, KGs are a powerful way to represent knowledge in multiple communities, including data mining, natural language processing, and machine learning. However, more recently, domain-specific KGs have emerged as a powerful technology, especially in industry. Although domain-specific, the semantics of such KGs may be broad, such as the products sold by Amazon, or relatively narrower, such as a COVID-19 KG or the LinkedIn social graph describing people, organizations, and jobs. In the rest of this talk, I will briefly provide an overview of how domain-specific KGs are constructed from text in state-of-the-art systems in academia and industry. A typical pipeline is constructed by first deciding on a domain ontology with subject matter experts, as well as by gathering the text or other corpus over which the KG must be constructed. Examples of text corpora are Wikipedia, Yelp reviews, news articles, proprietary corpora such as LexisNexis, and company documents, social media, and many others. After the initial KG is constructed using information extraction and other natural language processing techniques, KG identification is necessary to refine the KG. Last but not least, the KG needs to be supported by a storage and querying infrastructure that will power end user tasks and applications. Next, we quickly go over some of the more important steps in this pipeline. The first and perhaps most important step is construction of or selection of the domain ontology, which is the primary point of intersection between subject matter experts and AI experts and or knowledge engineers. Fortunately, such ontologies do not have to be constructed from scratch, as many fields have ontologies that have become standard. In biology and chemistry, for example, the gene ontology and PubChem are very well known, while friend of a friend is a simple yet comprehensive vocabulary designed for social applications. Next, using the concepts in the ontology, we must conduct named entity recognition or NER over the raw text corpus. NER is the problem of identifying spans of characters in the text, which are called mentions. An example of a mention is Donald Trump, who has been tagged as having concept type person. NER is usually the first and most important component of information extraction, which is well researched in the NLP community. Today, deep learning methods are commonly used for NER. Although performance is excellent on common categories like person and organization, NER may have to be specially trained for some domain-specific concepts. Even in this example, the performance is not perfect. For more complex domains, including finance and biology, using domain-specific features, as well as gathering enough training data and retraining a neural network may all be necessary to achieve adequate performance and quality. A more advanced step is relation extraction, which is important for obtaining the edges in the KG, but which typically yields lower performance than NER, even for common domains. One reason is that the two entities between whom the relation must be discovered may be far apart in the text. There may also be significant ambiguity. Deep learning is also used in NLP for relation extraction, but performance has still not caught up to NER. Beyond information extraction, other NLP modules like coreference resolution and entity linking may also be necessary to further clean up the KG and improve its quality. Coreference resolution, shown on the left, is the problem of linking together pronouns and other indirect mentions of an entity to a more unambiguous version, usually represented by a proper noun. Entity linking, shown on the right, requires an external knowledge base like Wikipedia or DBpedia, and is a problem of linking a mention to a canonical entry. Entity linking is usually possible only for well-known entities that are present in such knowledge bases, although domain-specific knowledge bases may also exist within an organization. Regardless, ambiguity can cause significant noise in entity linking, as well as coreference resolution. Even after the initial KG is constructed, it must be refined or identified. One of the problems that occurs is that the same entity may be represented in multiple different ways, such as Barack Obama and President Obama. Accurately identifying which pairs of entities are matching is called entity resolution and is a difficult problem. Similarly, edges may be missing in the KG, and some edges may be incorrect. Today, representation learning techniques using neural networks and KG embeddings like trans-E and graph convolutional nets are used for addressing these various KG identification problems. To recap, a domain-specific KG starts by assembling the domain model, which is usually an ontology, and the raw corpus over which the KG is constructed. The final KG, which may be noisy and incomplete, even after multiple refinement steps, needs to be adequately supported by a storage and querying infrastructure. Examples of such infrastructure include traditional relational databases like Oracle and MySQL, but these are less suited for graphs. Recently, graph databases like Neo4j have emerged as good options for storing and querying graphs, including KGs. Other examples include key value stores like Elasticsearch, but only if the ontology is relatively shallow and contains a few concepts. Cloud versions of graph databases, such as Amazon Neptune, are also available. Finally, as shown at the bottom of this pipeline, KG research across this pipeline spans multiple communities and allowing users to build end-to-end pipelines for specific domains and applications continues to be an active area of research. We close by identifying some frontier domains for domain-specific KG research and development in industry. Good examples, albeit not exhaustive, include manufacturing, law and health, and epidemiology. Another important domain or collection of domains is building KGs for social good, as evidenced in our own work and also in a report by McKinsey, which identified areas within AI for social good. In many of these areas shown on the left, KGs can play an important role. There are also numerous workshops exploring knowledge graphs for social good, many of which are domain specific. For academics and research-oriented practitioners, there are numerous surveys on the subject of KGs and domain-specific KGs, although some are more field-specific. Several book-level treatments are also available, including a 2019 book I wrote on domain-specific KGC and a comprehensive MIT Press KG textbook published earlier this year. Because of their interdisciplinary nature, domain-specific KGs are at the forefront and frontier of many application and research areas, including information retrieval, semantic web, recommender systems, knowledge graphs and data mining, and many more. I hope you will consider using them in your own field or organization. We also provide some specific references here where domain-specific KGs have potential, whether directly or indirectly. For more information on specific projects in academia, we encourage you to look at our funded group projects, almost all of which involve KGs in some capacity. We are also hiring students and postdocs in many of these projects. I would like to close by thanking many of our collaborators and funders in our many projects in domain-specific KGs, especially DARPA and IARPA. And now I would like to close and stop for questions. Thank you for listening and attending our session. Please feel free to connect with me directly on LinkedIn and/or to write me through email. Thank you.
Good day, my name is Olav Laudy, and I'm the Chief Data Scientist at Causality Link. In the next 12 minutes, I'd like to show you how we use our NLP platform to automatically generate Bayesian networks from text. This presentation is based on a pre-published paper, and I'll provide a link to the PDF later. In full disclosure, Causality Link is a commercial NLP extraction platform focused on financial text. Our customers have access to a real-time software as a service platform, as well as a data as a service platform that can be queried using SQL. Our platform reads financial text in 24 languages and translates them into English before processing them into an NLP pipeline. We process about 50,000 new texts per day from 9,000 sources across the world, and by now we have a 6-year archive of around 100 million articles. We focus on high-precision extraction on sub-sentence level. Suppose that you have a text that discusses the current state of the automotive industry. So you have companies mentioned like Ford, Tesla, and General Motors. It is not enough to simply tag the company in such an article. Also, it's not very useful to tag KPIs as revenue or profit without knowing the context. In our platform, we co-reference KPIs and events, meaning that if we find the word revenue, we extract it if and only if we can find the context for that revenue. For example, the context can be the revenue of Ford in the country China, or the sales for Tesla for the product Model 3. The company is called Causality Link because we believe we're unique in our ability to extract human expressions of causality. There's a lot of discussion around what true causality is. However, our platform is built with the idea that the human mind is very good in understanding causality. And as such, when an author writes that, for example, inflation goes up due to increased oil prices, we extract a causal pair, oil price impacting inflation, along with the context, such as date, location, authors, etc. When you then query the archive of 100 million text and ask, show me all the drivers of inflation rate, it will return a massive collection of causal pairs. Not only do we see the various drivers of inflation rate, but we see how the various authors express different opinions on how the same driver impacts inflation rate, and this over time. The Bayesian network that we automatically generate integrate all those different points of view into a single coherent collective point of view. Without further ado, let us jump into an example of the end result. This image depicts a valid Bayesian network that has been created from thousands of individual statements across hundreds of authors on the USA inflation rate and its most mentioned 5 drivers. It's a rather small network, but it's a fair start for a presentation. In a few slides, I'll demonstrate how the network is being created from data. However, let's first try to understand the network itself. Let's take the node USA unemployment as an example. Unemployment has 2 outgoing arrows, one pointing directly to inflation rate, the other pointing to macro consumer condition. This indicates that the unemployment is a driver for both the inflation rate as well as the macro consumer conditions. The color of the arrow indicates the sign of the relationship. If the arrow is green, it means the driver goes up. If the driver goes up, the target will go up. And if the arrow is red, it means if the driver goes up, the target will go down. For example, if the USA unemployment goes up, we expect the inflation rate to go down. Just for clarity, we do not determine the link or the direction of those arrows. This is something that arises from the collection of text. You can look at the Bayesian network by inspecting each and every link and determine if the color of the link makes sense, and then drill down into the underlying statements that make up the link. But another way to look at the Bayesian network is from a more global point of view. We see how the 5 drivers make sense and give rise to a probability of 0.8 that the US inflation rate will go up as per September 8, 2021. The strongest forces pushing up the inflation rate are, according to this model, the increasing world GDP as well as the increasing oil prices. Traditionally, Bayesian networks are created by experts, and even small networks like these would take a considerable amount of time to create, as experts would have to agree not only on the nodes in the network, but also on the existence, direction, and strength of the arrows. With our system, a network like this is created within minutes by automatically collecting all the expert opinions from text. A valid question, of course, is, does this network make sense? Is it true, if you will? On the previous slide, you saw a Bayesian network for a single point in time, but since we incorporate time information as context, we can generate Bayesian networks every day. And we created daily networks focused on company stock prices for many companies and subsequently used the outcome to paper trade or backtest that company in the stock market. On this slide, you see an example of a network for the stock price for the company ExxonMobil. On top, you see the network for 3 moments in time. And you see how the ExxonMobil stock price prediction ranges from 54% to 41% in March 2020, the middle of the COVID crisis. You even see how this is driven by the very low oil price of 18%. And you see the prediction coming back up to 65% in June of this year. On the bottom, you see a graph where the blue thick line represents daily probability for the ExxonMobil stock price prediction. Just to be clear, we compute a Bayesian network for every day, and that includes the newest data available that day. This may not only change the relationships in the network, but also may change the drivers involved in the network. As for the backtesting, the trading rules are very simple. If the probability exceeds 0.6, you buy the stock. If you see it drop below 0.55, you sell. And conversely, if the stock price, the stock prediction drops below 0.40, you short the stock. And when the probability comes back up over 0.45, you exit your short position. Those are indicated with the green and yellow boxes in the graph. Over a period of 2.5 years, you see how we make a profit of 86% on a stock that, after all, is fairly volatile and mainly trades sideways. A nice notion is how, prior to the COVID started, the stock price signal was negative enough to short ExxonMobil, leading to a considerable profit during the depth of the COVID crisis. Also, you see how since December 2020, the signal has been mostly positive, resulting in a very profitable long position. Note that in the computation of this Bayesian network, at no point in time we actually use the ExxonMobil stock price. As such, this is a fully unsupervised procedure based on text only. While this is an example of a single company, we have observed similar results with many other companies, and apart from single company trading strategies, we've also successfully deployed long-short strategies based on Bayesian networks. It's time to turn to the generation of those networks from text. Let's be very explicit about the data that has been used to create the networks. This table is a screenshot that I took from the Bayesian net article. It shows examples of the relation between the oil price and the USA inflation rate as described by authors. If you think about it, you would naturally assume that the relationship is always positive, as the oil price is contained in the basket of the inflation rate computation. Let's read the first sentence. With the inflation easing on the back of lower oil prices and falling commodity prices has allowed RBI la la la. You may almost read over it, but the first part of the sentence says, inflation is easing on the back of lower oil prices, meaning the author observed a lower oil price and as a result points to easing inflation. This is an example of a positive relationship where both trends of oil price and the inflation rate are down. Yet, authors try to give an accurate depiction of the state of affairs. For example, on the fourth line, we read, US consumer prices rose modestly last month, weighted down by falling oil prices, meaning the oil prices were going down while the consumer prices were going up. And a few down lines lower, we see the statement, in June, we saw an inflation slowdown despite the spike in oil prices. So again, an author tries to give an accurate depiction of the causal relationship where he sees the gas price going up, yet the inflation going down. Let's turn to a simplified example to understand how a Bayesian network comes about from text. Here we have the very simple case where as humans, we understand we need both matches as well as wood to make a campfire. But obviously this is unknown to a Bayesian network. For those that understand the mathematics behind the Bayesian network, we see that we need to assess the conditional probabilities indicated from the formula in red. In this slide, I've tried to illustrate how over time, different authors express their observed truth. One author may write, the matches lit the fire soon, and maybe the same author goes to a forest, comes back and sometimes later write, well, even though I brought matches, there was still no fire. Another author says, despite the lack of matches, there was still a fire. And then fully independent of those observations, we have the same or other authors describing the relationship between bringing wood and having fire. Now, the NLP process extracts all those causal expressions into single causal pairs, and you can aggregate those into two contingency tables displayed on the right. The top table displays the joint probability of bringing matches and having a fire, while the bottom table shows the joint probability of bringing wood and having a fire. We take those two contingency tables and then, using a minimization procedure, we create a Bayesian network that generates one coherent truth. In mathematical terms, we supply the joint probability of cause 1 or C1 and a target, C2 and a target, and we must build a joint probability table, C1, C2 and a target. Obviously, that joint probability table then must satisfy the Bayesian network structure. Finally, once we have that model, that is the relationships in the Bayesian network, we can score the model. We use forecasts for this that are also acquired from text. Our NLP engine recognizes whether a statement is about the past, such as the oil price rose by 5%, versus a statement about the future, such as we expect the oil price to have increased by year end. We compute the text-based forecast as the percentage of future statements that says this topic will go up. In our small example, we compute the percentage of authors saying there will be matches and the percentage of authors saying there will be wood. If both probabilities are low, this is as to say there will not be matches and there will not be wood. We then supply those probabilities to the trained Bayesian network and marginalize to the target. This results in a probability of having a fire being very low, and this is as to say there will not be a fire. This, in a nutshell, is what we apply to larger networks that I demonstrated earlier. An obvious use case for the Bayesian network is to use it as a prediction model, and the backtesting method shows that this works. However, there's much to say about the impact of NLP errors and the articles to consider for inclusion for the predictions and so on. We believe that our methods are also useful for the automatic creation of a global point of view. We believe that this is the first fully automated expert knowledge synthesis. It can serve as a collaboration model. Imagine looking at it with a group of experts. Rather than going through a dreadful exercise of building it from the ground up, it's automatically acquired from text, and then experts' time can be more efficiently be used to modify or curate the model. It then can be used to understand the sensitivities to the various factors and maybe later as a customized prediction model. Finally, we want to point out that if you're having a discussion on any financial or economic topic, arguments are seldom complete or coherent. While you may not want to put all your trust in a fully automatically generated Bayesian network, The least thing you can say is that it's based on a collection of thousands of statements across hundreds of experts, which makes it interesting to take into account at least. We somehow also came to appreciate the graphical representation of the Bayesian network as a high bandwidth communication tool, because it allows you to condense many discussions in a single image and have a very structured way to discuss every point. With that, I want to thank you for your attention. Again, my name is Olav. The first link points to a PDF of the paper. The second link points to my LinkedIn page, and the third link points to our company Causality link. Please feel free to ask questions after this session or get in touch with me via email or LinkedIn. I'll be looking forward to any interaction.
Good morning, good afternoon, and good evening, wherever you are. I'm Victor Chen. I am an associate professor in business and affiliated professor in data science at the University of North Carolina in Charlotte. It is my pleasure today to present my working project with Seetha Gopalakrishnan, a doctoral student in computer science at UNC Charlotte, and Gus Hampel, assistant professor in computational linguistics at the University of Arizona. Our research is on machine reading and a knowledge graph for enterprise performance management. So just give you a little bit of background about this research. Over the last decade, academics, policymakers, and business leaders have been encouraging a paradigm shift from an egocentric agency view centered around the investors or shareholder value primacy to an inclusive agency perspective that emphasizes multiple stakeholders' benefits, where stakeholder satisfaction with firm performance should concern broad well-being for not just investors, but also employees, customers, suppliers, and the society at large. The most recent example is the 2019 Statement on the Purpose of a Corporation, released by the Business Roundtable and signed by almost 200 CEOs of the largest US companies. If we extrapolate this shift even further, the rise of virtual platforms and the remote work technologies is growing an agentless blockchain type of complex co-working community in the future, where individuals and small teams become increasingly flexible to collaborate directly with one another on a virtual space as suppliers, colleagues, employees, contractors, customers, investors, and so on. However, this increasing complexity and a multidimensional objective function governing corporations is making the current information management system at most enterprises obsolete. Notably, most large organizations today have enterprise performance management or EPM systems centralized into the CFO's office, where financial data are aggregated from different functions and regions into a unified dashboard, just like the graph you see on the slide. However, non-financial objectives concerning stakeholders such as customers, like patient care satisfaction, product service quality, brand loyalty, and employees like job satisfaction, organizational commitment, mental health, etc., are typically disconnected in data silos in their own legacy systems. So is the domain expertise in people working on such data. So the knowledge about the underlying causes and effects relationships across different performance outcomes, stakeholder interests, and the overall strategic actions are obscure or missing in this process. In other words, there is an increasing gap between fragmentation of expertise and knowledge and the integrated need for enterprise performance management concerning different stakeholders' benefits. So our solution is to crowdsource the causal insights related to different stakeholders' benefits as enterprise performance outcomes and their underlying drivers inside outside an organization into a unified causal knowledge graph. And we do so by aggregating the theories and evidence from high quality research documents, including both inductive knowledge from audited documents such as company reports and a deductive knowledge from refereed literature in social, economic, and behavioral sciences, for example. So a causal knowledge graph we are generating is a visual representation of the concepts and the causes and effects relationships, which is not only intuitive for human decision makers to access using their fingertips, but also machine readable through, for example, Python packages of Neo4j drivers, do-wise, and so on, that connect graphs into structural equation models for data analysis. So the overall architecture consists of 4 components or steps. The first is annotation and reviews of research documents, highlighting strategically important business variables and performance outcomes. This process starts with manual coding by a large team of domain experts, such as doctoral students in business, organizational science, finance, management, and so on. This manually collected database itself is ready to be used as a knowledge graph for decision making. And we have made that available for certain topics. The second step is to use the annotation database as a training data to develop machine reading models to automate the process of text to knowledge graph transformation, which will be the focus of our presentation by Seetha later. The third step is to synthesize the knowledge graphs, multiple graphs extracted from different sources into a unified knowledge graph database, grounded in a predefined standardized taxonomy. The final step is to make the knowledge graph accessible for both researchers, like you and me, and the business decision makers. For instance, researchers could use the unified knowledge graph to map the theoretical pathways linking different variables from organizational behaviors to specific outcome variables. Whereas decision makers can use the knowledge graph database to work on their own data by developing causal graph-based statistical or machine learning analysis and identifying statistically most important pathways to optimize specific performance outcomes. So let me show you a short demonstration from a user's view. The first is a comprehensive knowledge graph on the causal relations among business and management variables. It is a visual representation of causal knowledge by integrating and reading extensively business research documents and the literature. For example, here you can use simple graphic query language to retrieve all the causal relationships related to economic well-being of your employees. Users can also narrow the search by industry, country, and year. And here's one example showing just one country, Turkey. The second technology is a machine reading system to automatically extract, deconstruct, and organize causal insights from users' own documents into structured data that can be uploaded and integrated with the knowledge graph database you just saw. Users can very easily upload unlimited volume of documents in PDF, for example, and user interface will automatically extract the useful causal insights, deconstruct those insights into causes, consequences, and their relationships, group similar concepts together into clusters, and then allow users to download the structured data in Excel table to be uploaded and integrated into the knowledge graph database. In other words, users can customize their own knowledge graph. Finally, the third technology is a graphic user interface to visualize the relative importance of different causal pathways. Users can upload their own data to quantify different causal pathways in this knowledge graph for them to understand what are the statistically most important drivers for their given set of performance outcomes. In a very straightforward way, the causal pathways, the drivers that explain the variations in such outcomes. And all these are done visually in a very intuitive way. And now let's turn this over to Seetha, who's going to dive deep into one particular component in this architecture, machine reading, to turn text into knowledge graph data.
In this project, we are concentrating on two main tasks, which are causality extraction and classification of variables based on a business taxonomy. Causality extraction is nothing but given a text document, we have to identify the sentences which have causal relations, and the second one is we have to extract the actual causes and the outcome from the classified sentences. So this first classification of causal sentence, we are finding whether if there is a causal connective present in a sentence. If at least one causal connective is present in a sentence, it will be considered as a potential causal sentence. The extraction of the causal cause and outcome from the sentence, we are approaching it as a named entity recognition problem and applying some deep learning models. This given example is taken from one of the manually annotated document. Here we can see that the beginning and the end of the causal relation is identified with the help of the tags. Similarly, this yellow part gives the cause, and the green part gives the trigger, and the blue part gives the outcome of the this sentence. Once this cause and the outcome are identified, the next task is we have to classify whether this cause and the outcome will belong to which of the category. By category, I mean in this paper cited here, they have given a business taxonomy which involves 3 levels of categories: the level 0, level 1, and level 2. In level 0, it will be categorized into whether it is a performance or non-performance category. In level 1, it will be categorized into whether it belongs to customer, investor, or employee or the society category. In level 2, similarly, they have 16 labels, 16 category. We have to classify whether this cause and the outcome belongs to which one of this category. That is the classification task. Before moving on to the machine learning model which we are applying for this project, I would like to introduce the data which we are using in this project. We are using two types of data. The first one is the academic data, and the second one is the company data. Academic data is obtained from the academic research articles which we obtained from the ISI Web of Science database. We have got 125 papers, and each of this 125 papers is manually annotated, and this we are using as the gold standard data. From the manually annotated data, we can understand that there are totally 689 concepts in the academic data. By concepts, I mean the total number of the causes and the outcomes present in the documents. The second type of the data is the company data, which we obtained by from the 10K reports of S&P company. So after manually annotating this 10K reports, we have got 21,163 concepts. So both these data we are applying for all the tasks. So this part explains the machine learning models that we are applying for the tasks specified in the previous part. The first task specified is the causality extraction. As I specified previously, we are approaching this as a named entity recognition problem. So the input to the machine learning model will be the word level tokens of the sentences, potential causal sentences, and the labels will be the named entities. So this BERT, named entity recognition, and the BiLSTM are the two models which we are trying to apply now. We are also planning to use BiLSTM with CRF in the future. For the next task is the classification of variables into a business category. For that, we have actually tried applying 13 machine learning models, which are listed here. So for all these machine learning models, we use stratified k-fold to split the data into train and test data with a seed value of 1 to 4. Whatever results I am presenting for this classification task is an average of the seed value of 1 to 4. So as you all can see, we have applied logistic regression with count vectorizer, which uses TF-IDF transformer. So this random forest, XGBoost, SVM, and multinomial naive Bayes, we are using the libraries from the scikit-learn. Apart from that, we are using some latent features like fast text, which is a Facebook model, and fine-tuned BERT. We have also tried applying some contextual embeddings like BERT, Elmo, along with the logistic regression. Apart from all these available models, we have also tried to expand the length of the concepts, which I said previously. In the previous slide, I explained concepts means the causes and the outcomes. So we try to expand the length of this concepts, causes and the outcomes, by trying to find whether there is any sentence which is related to that particular cause or outcome in the entire academic and company data. If there is a sentence which is related to that particular cause or outcome, we retrieve that particular sentence and append it with that cause or the outcome. That is how we are trying to expand the length of that concept and try to apply count vectorizer and logistic regression. So these are the models which we try to apply. So here are some results which we have obtained with the classification of the variables into a business category. So as I specified in the previous slide, we have applied 13 machine learning models. So in this table, we have listed only the models which are performing better in all the 3 levels. So this table have the results of level 0 labels, and this is for the level 1 and this is for the level 2. So as I specified previously, level 0 is performance or non-performance category. Level 1 is customer, society, or employment, or investor category. 4 categories are there, and in level 2 we have 16 categories. So if you can look into the results, we can understand that in level 0 and level 1, logistic regression is logistic regression along with the count vectorizer is performing better than any other model. And in level 2, we can see that spaCy embedding with logistic regression is performing better. So all these contextual embeddings is not performing better than the logistic regression with count vectorizer. The reason behind this may be because we haven't tried training the embeddings for this particular concepts. We just use the pre-trained embeddings which is available. That may be a reason for this low performance. One other thing is apart from this, we have also tried applying company data for company this classification models for the company data. As a first step, we first applied logistic regression with count vectorizer because that is the best performing model with the academic data. So this result given here is by applying logistic regression along with count vectorizer. And we are trying to improve the F1 score of this particular company data classification by applying many more models. One other thing I would like to specify here is in the previous step, I told you that we have expanded the corpus by finding the similar sentences to the causes and the outcomes. So the results of these two indicates that for the academic data, appending sentences from the company reports give us some higher F1s, gave us some higher F1 score compared to the other one. So this indicates that this company report and the academic data, both of them are related to each other.